Hi class. In this lecture here, we want to talk about area, Riemann sums, and the definite integral or definite integrals. And this lecture here is going to be pretty intense in terms of theory, and some of the examples we do, or one of the examples we do, are going to be pretty challenging. But what this lecture does here is it helps set up one of the big applications of integration, and that's finding area under a curve. And if you remember when I introduced the topics of calculus way back in our first couple lectures, I said, look, there's two classic problems for calculus, right? There's the tangent line problem and the area under the curve problem. And we saw that differentiation helped us find the tangent, helped us solve the tangent line problem. Now what we're going to see here is that integration, what we began talking about in the previous lecture, is going to help us solve or find area under the curve. Okay, so this lecture here, we're going to be doing a lot. Okay, I'm going to talk about how you use sigma notation to write and evaluate a sum. We're going to approximate the area of a plane region. That's going to be using those rectangles that I talked about when we were doing area under the curve. Then we're going to find the area of a plane region using limits. This is going to be really complex, and I'm only going to do one example of this. Okay. And the one example here, you're going to see it's really difficult, and there's a lot of steps to it. It's very easy to make sense. So I want to show you how you find area under the curve using limits and this plane, using the limits to find the area in a plane region, and it's going to help us set up and understand why we're going to need to use integration because we're going to need an easier method. Then we're going to talk about understand the definition of a Riemann sum. We'll talk a little bit about definite integrals and what type of limit it is, and then we're going to understand the definition of definite integral. So there's a lot going on, and you can see here there's going to be a lot of formulas here, a lot of definitions going on. I'm going to do my best to explain this all to you. Okay, so let's jump in. Let's first talk about sigma notation. Okay, so sigma notation, all right, this is the notation of a sum. So the sum of n terms, and the terms are a sub 1, that's the first term, a sub 2 is the second term, a sub 3 is the nth term, all the way to a sub n. So n could be 5, it could be 10 terms, it could be 100 terms. Is written as, this is a capital sigma in the Greek alphabet, so it's the sum, and it says I starts at 1, and it goes to n. And what you do is you increment I. So you keep adding 1 to it. So I goes from 1 to 2 to 3 to 4 to 5 until you get to n. And we write this as a sub I. And what this is telling you is look, the first term, wherever you see an I, replace it with 1. The second term, wherever you see an I, replace it with a 2. And then you're going to keep going. The third term, okay, replace it with a 3, and so on until you get to the nth term. And this is where I is the index of the summation, and a sub I is the ith term of the sum, okay? And the upper and lower bounds of the summation are n and 1, okay? So this is the upper bound. This tells you what to stop at, and the lower bound down here tells you where to start at. All right, so let's do some pretty simple examples of this, just so you could see, how to use this sigma notation. All right, so in each of these examples, what we want to do is we want to find the sum. So here will be the first one. I starts at 1 and it goes to 4 of just I. Okay? So look, this is what happened. Wherever you see an I, you start at 1. So you go to 1. And then you're going to add to it. Now I is going to go to 2. Now I is going to go to 3. And then I is going to go to 4, and that tells you to stop right here. And then you just find the sum. 1 plus 2 is 3, plus 3 is 6, plus 4. This sum is 10. Okay? Let's try this one. The sum of I is equal 1 to 5 of I squared. All right? So start at 1. So this would be 1 squared. Plus, and now the index is gonna increase to 2, so 2 squared, because I'm replacing the value in for I. Plus 3 squared, plus 4 squared, And then I get to, oh, I'm going to get to 5, and then I'm going to stop. Plus 5 squared. So now let's just figure out what the sum is. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. And 5 squared here gets me 25. Right? Now if you add this up, this is how I do it. 4 and 16 is 20. 9 and 1 is 10, that's 30. And then 30 plus 25, that's 55. All right, so it turns out that there are some tricks that you can use to help find sums. And we're going to use some of these tricks in the coming slides. And they're going to be really important, like some shortcuts for sigma notation here. And so here are some summation ones here. All right, if you have the sum as I is equal 1 to n of a constant, okay, so this would be something like I is equal 1 to 3 of 5. What this is saying is, look, the n is the top here. This is saying this is equal to c times n. Well, the constant is 5 times 3. This would be 15. The reason being is because this is just 5 plus 5 plus 5 is 15. Now look, this is saying the sum of I, which is what we have here, from 1 to n, so kind of like this, the sum I is equal from 1 to 4 of I. This is saying it's equal to n, so this would be 4 times n plus 1, which is 4 plus 1, divided by 2. Well, let's see. 4 times 5 here, because 4 plus 1 is 5, is 20 over 2, which gets me 10, which is what we got when we did it by hand, right here. So you can use this little trick here to help you. And now look here, I squared, all right? The sum of I squared. So I is equal 1 to n of I squared is n times n plus 1 times 2n plus 1 divided by 6. So this is I is equal 1, well, let's verify this. I is equal 1 to 5 of I squared. So my n here is 5. So this is 5 times 5 plus 1 times 2 times 5 plus 1. And it should be all divided by 6. Well, let's see. This is 5 times 6. 2 times 5 is 10. Plus 1 is 11. All divided by 6. Well, look, the 6's cancel out. You're left with 5 times 11, which is 55, which is exactly what we got when we did it by hand. So whenever you see the sum of I squared to some value, you can use this formula here, and we will, and we will later on in class. All right, so now we kind of have some understanding of sigma notation. Let's set up the problem we're going to work on initially here. Okay, so here's what I want to do. I want to approximate the area under the curve of this function. F of x is equal to negative x squared plus 6. And I want to do this above the x-axis, okay, in between x is equal to 0 and x is equal to 2. All right, so let me sketch here just so you can see the area we're trying to find. So 1, 2, 3, 4, 5, 6, 1, 2. Okay, so look, when I want to be between x is equal to 0 and 2. So when x is equal to 0, it's 6. When x is equal to 1, you get 5. And when x is equal to 2, let's see, 2 squared is 4, but you make it a minus, you get 2. So look, here's the curve, okay? Kind of looks like this. I want to find this area here. Okay, I want to find this. I'll even shade it in. I want to find this area. So it's like, okay, well, you know, how will I do this? How will I find this area? Well, so the way we talked about it is, well, like there's no geometric formula for this. Okay, so what we're going to do is we're going to approximate the area by filling it with rectangles. Okay, I'm going to approximate this area by filling it with rectangles. And so what I'm going to do in this next slide here is, okay, it's like, okay, all right, well, let me say I want to fill this with, like, say, let's say 4 rectangles, okay? And I want to figure out, you know, what that approximation will be, all right? And it's going to be a little tricky, okay, to do this, all right? So we're going to approximate that red shaded area there with rectangles. All right, so let's go to the next slide here, and let's do it with 4 rectangles, as I said. Okay, so let's approximate the area under this curve of f of x is equal to negative x squared plus 6 above the x-axis between x is equal to 0 and x is equal to 2 using 4 rectangles. And I want to highlight this. This is important here. And the rectangles are all going to be of equal width, okay? So I'm going to attempt to sketch this again. Sorry for my little sketches off a little bit here. I'm going to redraw this. This looks terrible. Okay. Here's x. Here's my f of x. 1, 2, 3, 4, 5, 6. 1, 2. Okay. So this curve is going to look roughly, I know that's terrible sketch there, but you got the idea. Okay, there's the curve. All right, so what I want to do is I want to find the rectangles to be of equal width. Okay. So the width of a rectangle. The notation you're going to see is it's going to be b minus a over n. Okay. And let me explain what that. A and b here are the starting values of the x value bounds. So this is a and this is b. So this would be 2 minus 0. In n here, n is the number of rectangles. Okay, n is the number of rectangles. So how many rectangles did I want? I wanted 4. So this is 2 over 4, or 1/2. Okay, which totally makes sense, right? That we would want the width of each of these rectangles to be 1/2, right? So, because if I wanted to fit 4 of them between 0 and 2, that would be 4, you know, times 1/2. So you get 1 here, 1 here, 1 here, and 1 here. Okay, so now here's what I'm going to do. I'm going to draw the rectangles starting at x is equal to 0 with 1/2. Okay, so here's, you know, between 0 and 1 is 1/2 right here. Oh, gosh. Very hard to draw these rectangles with the stylus. So here's the first rectangle. Here's the second rectangle. Here's the third rectangle. And then here's the fourth rectangle. Okay, so I have 4 rectangles. And what you see here, okay, so you're going to sum, okay, so the approximate area is going to be equal to the sum. So the sum, so we're going to use this sigma notation here, the sum of the areas of the rectangles. Okay, well, so it's the sum. So how many rectangles do we have? We have 4 rectangles. So I'm going to start I is equal, the first rectangle is 1, the first rectangle 1, and then I'm going to sum to 4. All right, and the area of the rectangles are given by the height times the width, or length times width, right? I'm going to put height. All right, well, do you notice that the rectangles have different heights here? Boom, 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 boom. Well, what is determining their height, okay? What is determining their height is the function, okay? The function f of x. So height is determined by f, and I'm going to put something in there. It's going to be a little interesting, okay? And the width we saw here, the width is just 1/2, right? Well, look, the first height occurs at 1/2, right? X is equal to 1/2. The second one occurs at x is equal to 2 times 1/2, okay? Then 3 1/2s, then 4 1/2s. So notice 1, 2, 3, 4. So this is going to be 1/2 times I. So I have to take 1/2 times I and now plug it into my function. So this is I is equal 1 to 4. Now f of 1/2 times I. Okay, so be careful. So this is negative 1/2 I squared plus 6 times 1/2. All right, we have to clean this up a little bit, right? So let me square the 1/2. So this is the sum. I is equal 1 to 4 minus, this is 1/4 I squared plus 6 times 1/2. All right, let me distribute the 1/2. So this is the sum of I is equal 1 to 4, distributing the 1/2. So you get minus 1/8 I squared plus 3. All right, so the way you're actually going to break this up, this is cool. You're going to split this sum into 2 terms, okay? And you can do that. So it's the sum, I is equal 1 to 4 of minus 1/8 I squared plus the sum, I is equal 1 to 4 of 3. Now this constant, 1/8, minus 1/8, you can even factor that out. So it's minus 1/8, the sum of I squared plus the sum, I is equal 1 to 4, I forgot that over here, of 3. All right, well, what is the sum of from 1 to 4 of I squared? Well, that's 1 squared plus 2 squared plus 3 squared plus 4 squared. That gets you 30. So this is minus 1/8 times 30. Plus, well, this is the sum of a constant, right? So this is just 4 times 3, which gets you plus 12. So this is minus 30 over 8 plus 12. So that, even simplifying this, right? This simplifies to minus 15 over 4. Then 12 you could write as 48 over 4. So my area here, approximate, is 33 over 4. So the sum of the areas here is 33 over 4. But do you notice, like, that I underrepresented the area, right? Like, there's all these gaps in here, okay? Like, I missed this, I missed this, I missed this. So this is less than the real area. Right? And then it was a lot of work just to get, something that wasn't even the right area here, right? So it's like, oh, how can we find what the real area is? So the way you would actually find the real area, okay, is you need more rectangles, right? Make more and 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 more rectangles, right? So the way you're going to do that is, you're going to decrease the width, right? And you want the width to get infinitely small, okay? So, but the problem is you can't have a width of 0, right? You can't divide by 0. But what you can do is you can evaluate a limit and look what happens as the number of rectangles goes to infinity under there. Okay, so this is where it gets very, very complex. And this is going to be the one we're going to actually find the real area under the curve here, okay, using the limit process. All right, so let's go to the next slide. It gets very, very hard. All right, let's find the area under the curve of f of x is equal to negative x squared plus 6 above the x-axis and between x is equal to 0 using limits. Okay. So again, I'm going to sketch it just so you can see what's going on here. Okay. So what I'm going to do is I'm going to fill this with rectangles, okay? You're going to fill with rectangles of equal width. Okay? So I'm just going to sketch a rectangle here. Okay? This rectangle, what is the width of it, right? The width, we're going to denote as delta x. It's the change in x to go from here to here. And this is always b minus a over n. Okay? So what I'm going to do here is I'm just going to let n be the number of rectangles, right? And then what I'm going to do is you'll see here I'm going to take the limit as n goes to infinity. Okay? So b minus a, again, this is still 2 minus 0 over n. So the width of each of my rectangles is 2 over n. And like if you look back, right? It was the same thing here. It was 2 over, in this case, our n was 4 because I only wanted 4 rectangles. So then what we're going to see, and this is where it gets crazy, okay? The area equals the limit as n goes to infinity, because I want to have an infinite number of rectangles under there, because I want the the width to go to 0. I is equal 1 to n of the height, okay? Well, what was the height? It was 1/2 I. So it was whatever your width was times I. So my width here is 2 over n. So it's f of 2 over ni times the width. And the width was right here. In this case, it was 1/2, but over here, the width is 2 over n. All right, we're doing it. So let me help clean this up here. So this is the limit as n goes to infinity of the sum of I is equal 1 to n f of, so wherever I see an x, I'm now going to plug in 2 divided by n times I. So this is minus 2ni squared plus 6 times 2 over n. So this equals the limit as n goes to infinity of the sum of I is equal 1 to n. So I have to square this, right? So this becomes 4 over n squared. So this is minus 4 over n squared I squared plus 6 times 2 over n. So there's a lot going on. You have to be very, very, very careful. All right, so I'm going to distribute here. So this is the limit as n goes to infinity of the sum of I is equal 1 to n. Distribute here, so this becomes minus 8 over n cubed I squared plus, and then distribute here, 12 over n. All right, so all I've done is I've just basically done the algebra part here. Okay, so now I'm going to need to do a little bit of some actually some pretty cool stuff here um, to be able to evaluate this limit. Okay, like there's an inclination to just be like, oh, just n goes to infinity. This is 0. This limit doesn't exist. But don't forget you have this n in the summation sign. So before we evaluate the limit, what you need to do is you need to simplify the summation. All right, so what I'm going to do is I'm going to move this to the next slide. I'm going to recopy this limit, and I'm going to show you how we're going to simplify it. All right, so I'm going to bring this over to the next slide. So this was the limit as n goes to infinity of the sum of I is equal 1 to n of negative 8 over n cubed times I squared plus 12 over n. All right, so you're gonna leave the limit alone here. So the limit, this will be the last thing you're gonna look at as n goes to infinity. So I'm gonna break this up. This is the sum. I is equal 1 to n of minus 8n cubed times I squared plus the sum of I is equal to 1 to n of 12 over n. I'm going to look, this is where it gets confusing. So the summation only works with things with I, okay? So that's the only thing you need to increment. So this minus 8 over n cubed is just a constant, right? So this is the limit as n goes to infinity. I'm going to factor out this, so this minus 8 over n cubed times the sum of I squared as I goes from 1 to n plus the sum I is equal 1 to n, and this is just a constant, right? Well, what is the sum as I is equal 1 to n of I squared? Well, let me go back. It's just this right here. I is equal 1 to n of I squared is just this formula right here. N times n plus 1 times n plus 2 all over 6. So I can replace this right here don't forget you have this minus 8 over n cubed, right? This entire thing, this I squared, gets the sum of I is equal 1 to n of I squared literally gets replaced with n times n plus 1 times 2n plus 1 all over 6 plus, now this is just a constant. So it's the constant times whatever number's up here. Well, it's n. So plus 12 over n times n. All right, now we just need to clean this up. This is where it gets crazy, okay? So the limit as n goes to infinity, you're going to FOIL this out, okay? So this is minus 8 over n cubed times, this is going to FOIL to be 2n cubed plus 3n squared plus n all over 6. And then n cancels here, plus 12. All right, what you now need to do, and this is where it gets even harder, like you can move this 6 over here, okay? A lot of algebra you're seeing here, like this is a lot going on. I'm gonna treat this and split it and like multiply in this way, right? So like I can bring this 6 out here, and this becomes -4/3 n cubed times n cubed plus 3n squared plus n plus 12. Now distribute, right? When you distribute here, the n cubed cancels, so you're left with -4/3. Distribute here, the 3's cancel, but remember you have n squared divided by n cubed, so you're left with -4/n. And then distribute here, you're left with -4/3n squared. And then you have this plus 12. Oh, look at this. This is wild. This is just amazing here, right? So, oh no, I'm sorry, I forgot the 2 here when I distributed here. So yeah, I'm sorry. So when I distribute, it's actually -8/3. Sorry, almost made a little mistake. I forgot that 2 there. Okay, so look, the limit as n goes to infinity. This goes to 0, this goes to 0. So it's just -8/3 minus 0 minus 0 plus 12. So this is just -8/3. 12 becomes 36/3. And the correct actual area under this curve is 28/3. That's the actual area. And now look, this was really hard, okay? This was really, really hard. There was a lot going on here, okay? And you even can see I almost made a little mistake because I forgot this the 2 here, almost, okay? So there has to be an easier way, right? Like this, I'm only going to even do one example of this. Like, look at all this work that went into finding the area under the curve using limits and rectangles, right? It was like really, really hard, right? And so we're only going to do one example of this, okay? And we're going to spend our time focusing on the easier way to do this, all right? So there has to be an easier way. So like if you remember when we did the tangent line problem, we used the limit to find the slope of the tangent line, and some of the limit stuff was really hard, and it was like, wow, what do we do? There has to be an easier way, and we introduced the derivative, right? And so there's an easier way to evaluate these limits, okay? And it's going to be using what's called the definite integral. And so I want to set up just end this lecture talking about a little theory and notation that you're going to see in the next lecture. Okay, so there has to be an easier way, and yes, there is. So this was introduced by a mathematician called Reimann, and this is what's called a Reimann sum. So this is the notation you have to get used to seeing. So if you notice all the problems I've done, I said the rectangles have to be of equal width. Well, why, right? Why do that? So it turns out that the subintervals here, they do not need to be of equal width of these rectangles. So if we consider this region here, f of x is equal to the square root of x, all right? And I want to be bounded between the x-axis and x is equal to 1. So there's 2 types of rectangles you can do. You can use what's called inscribed rectangles, which is what I've been doing here, where I underestimate the area. And then you could use these outside rectangles like this that overestimates the area. Doesn't matter, okay? So this mathematician Reimann said, okay, I'm going to introduce this concept of not using equal size rectangles. All right, so here's the definition of what we call a Reimann sum. So let's let f be defined on the closed interval from a to b, and let's let delta be a partition on a to b. Okay, so all of these rectangles is the partition, okay? Given by this, x sub 0 is less than x sub 1, less than x sub 2, all the way less to x sub n, okay? And this is where delta x sub I is the width of the ith subinterval, all right? If c sub I is any point in that ith interval, so c sub I is, any point in this interval down here, somewhere between it, okay, then the sum as I goes from 1 to n of f of c sub I times delta x sub I is what's called the Riemann sum of the partition delta. All right, just whenever you see this, okay, this notation here is what's called a Riemann sum. All right. And what you need to know here, just remember, is like, okay, I'm still using rectangles. All right, I'm still using rectangles here. All right, but the rectangles don't have all the same width. That's fine. So the width of the largest subinterval of this partition is the norm of the partition. It is denoted by this, okay? Double line, or the magnitude of delta here, okay? If every subinterval is of equal width, okay, then the partition is regular, and the norm is just denoted by b minus a divided by n, which is what you've been noticing I've been using, okay? But so here again, we're not going to use this equal width rectangles. So then what happens here, okay, is you can evaluate this limit using what's called a definite integral. All right, so this is what we're going to spend the next lecture on after this, definite integrals, okay? So if we let f be defined on the closed interval from a to b, and the limit of the Riemann sum over partition delta. So look, remember this right here is the largest partition, width of the largest partition. So we look at the as that width goes to 0, all right, of the sum of I is equal 1 to n of f of c sub I delta x sub I, okay, because that now the width is going to 0, all right. We're looking here now, instead of as the number of rectangles go to infinity, we look as the width goes to 0. If this limit exists, then what we say is the function f is integrable, all right. You can find the integral on a to b. And this limit, so no longer will we be using the limit to evaluate this. We're going to be using what's called this definite integral. And you'll notice that it has the integral sign of your function f of x dx. And the only thing that's different is you have these what are called bounds of integration, okay, or limits here. You have the a and the b. And remember, we've seen a to b. It's where the x is starting and where it's ending. All right, this limit is called the definite integral of f from a to b. All right, the number a is the lower limit or lower bound. You'll hear me interchange that. Of the integration. And the number b is the upper limit or upper bound of integration. And I'm going to show you, right? We know how to, we learned in the previous section how to evaluate. So in previous, we learned how to the integral of f of x dx, right? This was equal to f of x plus c. So now what's different here is I'm going to show you how to evaluate this later on, okay? Not in this lecture, in a coming lecture. I'm going to show you convenient methods for calculating this for continuous functions, okay? So for now, we're going to use the limit definition, or as you saw, but going forward, no longer use the limit definition. It's like, yes, okay, we won't have to do this crazy, this is a lot of crazy work here that I've just done, okay? And so here's some quick properties of it, and then in the next lecture, I'm going to show you how to evaluate these. Okay, so first off, if f is defined at x is equal to a, if you integrate from a to a of that function, that's just 0, okay, because there's no width there, it's just from a to a. All right, if you can find the integral on a to b, then if you go the integral from b to a, or a to b of f of x, this is equal to negative the integral from a to b here. So notice that when you flip the bounds, it was b to a, and now you're going a to b, it just changes the sign. All right, again here, if f, you can integrate it on 3 closed intervals determined by a, b, and c. If you go the integral from a to b of f of x dx, this is equal to the integral from a to c of f of x dx plus c to b f of x dx. Okay, so long as these two, the upper bound here and here are the same, and a to b are the same here, these two integrals are equal. Okay, here are some other important ones that we'll use a lot of. Okay, if you can find the integral of f and g on a to b, and k is a constant, okay, then the functions k times f and f plus g are also integrable on a to b. And if you have the definite integral from a to b of k f of x dx, what this is saying here is you can factor out the k and then find the integral. Okay, constants can be factored out. And that's okay. And then also if you have the definite integral from a to b of two functions, f of x plus or minus g of x dx, what you can do here is you can evaluate the definite integrals separately of the two. That's what this is saying. Okay. So you can find this as the definite integral from a to b of f of x dx plus or minus the definite integral from a to b of g of x dx. All right, so there was a lot in this lecture here. Okay, there was definitely a lot. And what we're going to do, all right, you're going to see this in the next lecture. I'm just going to show you how to evaluate this definite integral very, very easily. Okay, so don't worry so much about this limit process. It's like drinking from a fire hose. There's a lot going on here. Very easy to make a mistake. You know, I'm going to show you the rules to be able to evaluate this integral right here. Okay, so next lecture I'm going to show you what this equals. And it's going to be what's called the fundamental theorem of calculus. All right, class, as always, let me know if you need anything.